So hello everyone, today we will discuss about increasing and decreasing function. So let us start with the definition of the increasing and decreasing functions. Increasing and decreasing function. So let us start with the definition. Let f be a real valued function, and I be an interval contained in the domain of the function. Then f is said to be first increasing on the interval I. If x1 less than x2 implies that f at x1 less than equal to f at x2 for all x1 comma x2 belongs to the interval I. If we have 2 points x1 and x2 such that x1 less than x2, if they will imply that f at x1 less than equal to f at x2 for all x1 x2 belongs to the interval I, then we can say that the function f is increasing on the interval I. So second definition, f is said to be strictly increasing on I if x1 less than x2 implies that f at x1 less than f at x2 for all x1 comma x2 belongs to the interval I. If x1 less than x2 implies that f at x1 less than not equal to sign f at x2 for all x1 x2 belongs to the interval I, then we can say that the function f is strictly increasing on the interval I. So let us move toward the definition of third. So decreasing on I if x1 less than x2 implies that f at x1 greater than equal to f at x2 for all x1 comma x2 belongs to the interval I. If x1 less than x2 implies that f at x1 greater than equal to f at x2 for all x1 comma x2 belongs to the interval I, then we can say that the function f is decreasing on the interval I. So fourth one, f is said to be strictly decreasing on I if x1 less than x2 implies that f at x1 greater than f at x2 for all x1 x2 belongs to the interval I. If x1 less than x2 implies that f at x1 greater than f at x2 for all x1 x2 belongs to the interval I, then we can say that the function f is strictly decreasing on the interval I. So as we have seen four definitions, what is increasing function, strictly increasing, decreasing function and strictly decreasing function. Now we will move towards another definition, which is monotonic function. A function f is said to be monotonic on the interval I if it is either increasing or decreasing throughout the whole interval. Yes. What is monotonic function? A function f is said to be monotonic on the interval I if it is either increasing or it is decreasing throughout the whole interval. Means if the function has same behavior through the whole interval, then we can say that the function is monotonic function. For example, we know that the function e raised to the exponential function and the function fx is equals to gx is equal to log x are these both functions. We know that these both functions increases through in its domain, so these functions are monotonic functions. Now I will plot some graphs, then I will plot some graph. Through the graphs we will understood that which function is increasing or decreasing. So let us plot some graphs of the function. First, this is x-axis, this is y-axis. This is x-axis, this is y-axis. Third one, this is x-axis, this is y-axis. Fourth one, this is x-axis, this is y-axis. This is our x-axis and this is our y-axis. So first graph is this. We will understand this graph is the graph of the increasing function or decreasing function. So what we will do for the increasing and decreasing function, we will take for reference, let us take this point as x1 and this point as x2. So as we can see that x1 is less than x2, then this is the value of the function at x1 and this is the value of function at x2. We can see that the value of the function at x1 is less than the value of function at x2. If we will take this point as x1, then this is the value of the function at x1, so we can see that the value of function at x1 is equals to the value of function at x2. So equality also holds there. So x1 less than x2 implies that f at x1 less than equals to f at x2. So this is the condition of the increasing function. So we can say that this is the graph of the increasing function. So similarly, for reference, we can take this point as x1 and this point as x2. So we can see that this is the value of function at x1 and this is the value of function at x2. So we can see that x1 less than x2 implies that the value of the function at x1 is less than the value of the function at x2. So this holds for any x1 x2 this holds for any x1 and x2 through the domain of the function. So this is and we know that this is the condition of the decreasing function. So we can say that the function is decreasing function. Sorry, strictly not decreasing, strictly increasing. Strictly increasing, and this is increasing. Similarly, for the reference, we can take this point as x1 and this point as x2, and x1 is less than x2 implies that this is the value of the function at x1 and this is the value of the function at x2. From the graph, we can see that the value of function at x1 is greater than the value of function at x2. If we will take this point as x1, not this one, then what we can see that the value of the function, this is the value of the function at x1, the value of function at x1 is equals to value of function at x2. So equality also holds there, and this is the condition of the decreasing function. So we can say that this is the graph of the decreasing function. Decrease. So Similar again, we can take 2 points. This is, let us say this as x1 and this as x2. So we can see that this is the value of function at x1 and this is the value of function at x2. So x1 less than x2 implies that because the value of function at x1 is greater than the value of function at x2. And we know that this is the condition for the function to be strictly decreasing function. So this is the graph of the strictly decreasing function. Strictly decreasing. As we can say that we can break this interval in two parts. First, this is the first interval and this is the second interval. We can see that in this interval the graph the function is increasing, and in this interval the function is decreasing. So we can say that the function is neither increasing nor decreasing in this interval. So this function is neither increasing nor decreasing. So neither increasing nor decreasing. Now we will take an example and we will try to find out whether the function is increasing or decreasing. So let us move towards the example. Let f be a real valued function. Real valued function given by fx is equals to 2x plus 3 on r. So we will try to find out that the function is increasing or decreasing. So let us take 2 point x1 and x2 from the set of real number, because we have to check on the set of the real number whether the function is increasing or decreasing. So let us take 2 point x1 and x2 from the set of real number such that x1 is less than x2. So now we have condition that x1 is less than x2. So from here we can say that 2x1 less than 2x2 because if we multiply both sides of the inequality, then inequality will remain same. And from here we can say that 2x1 plus 3 less than 2x2 plus 3. This is nothing the definition of the function at the point x1, and this is nothing the definition of the function at x2. So we can see that f at x1 is less than f at x2. From starting we suppose that x1 is less than x2, and we have proved that f at x1 less than f at x2. So hence x1 less than x2 implies that f at x1 less than f at x2. So this is the condition of the strictly increasing function. So fx is strictly increasing on R, on the set of real number R. So till now we have covered that what is increasing function, decreasing function. Through the graph we saw that what is increasing and decreasing function, and we also have done a example. So now we have seen that how we can check the function is increasing or decreasing on an interval. Now we will see that how a function is increasing at a point. Now means we can when we can say that the function is increasing or decreasing at a point. So let x0 be a point inside the domain of the domain of the function f, then f is said to be increasing, strictly increasing, decreasing, strictly decreasing, strictly decreasing at x naught if there exists, this is the symbol of there exists, an open interval I such that f is increasing, strictly increasing, decreasing and strictly decreasing on the interval I. We can say that the function f is increasing or decreasing at the point x naught if there exists an open interval I such that the function f is increasing, strictly increasing, decreasing or strictly decreasing on the interval I. Means if the function is increasing or decreasing at in the interval I, then we can say that the function f is increasing at the point x naught or decreasing at the point x naught. Now there is an important point that we should note. What is the important point? An important point. It should be noted that we can talk about monotonicity of fx at x is equals to a only if it lies in the domain of the function without consideration the continuity and differentiability of the function fx at x is equals to a. This point will say that the point will say that the function f at x is equals to a lies in the domain of the function f. It can happen that the function f is neither continuous nor differentiable at the point x is equal to a. I will draw the graphs of the function at which the function is increasing, but it is neither continuous nor differentiable at the point x is equals to a. So we can understood this by the help of the graph. So first, second, third, fourth. This is x-axis, this is y-axis, this is x-axis, this is y-axis, this is x-axis, y-axis, this is x-axis, this is y-axis. So this is the point x is equals to a. This is the point x is equals to a. This is the point x is equals to a. This is the point x is equals to a. We can see that this is the graph of the increasing function, and the function is increasing at x is equals to a, but there is a sharp corner at the point x is equals to a, and we know that the function is not differentiable at sharp corner. So we can say that the function fx is increasing at the point x is equals to a, but it is not differentiable at the point at x is equals to a. In the second graph, we can see that the function is not continuous at the point x is equal to a because there is a discontinuity, but the function is still increasing at the point x is equals to a. In the third graph, we can see that this is the graph of the decreasing function, and the function is decreasing at the point x is equals to a, but there is a sharp corner at the point x is equals to a, so the function is not differentiable at the point x is equals to a. In the fourth graph, we can also see that this is the graph of the decreasing function, and the function is not continuous at the point x is equals to a. So it is not necessary that the point at which the function is increasing or decreasing, the function is continuous or differentiable at the point x is equals to a. So till now we have covered that what is increasing and decreasing function on an interval I, and how we can check whether the function is increasing or decreasing at the point x naught. Now we will see how derivate help us to identify the function, whether the function is increasing or decreasing. So how derivate helps us to identify whether the function is increasing or decreasing. We have a theorem which states that if f dash x greater than 0 for all x in the interval excluding the endpoint, and f is continuous on the interval, then f is strictly increasing. Similarly, we can also say that if f dash x less than 0 for all x in the interval excluding the endpoints, and f is continuous on the interval, then f is strictly decreasing. The theorem states that if f dash x greater than 0 for all x in the interval, and f is continuous for f dash x greater than 0 for all x in the interval excluding the endpoint, we can exclude the endpoint, and f is continuous on the interval, then f is strictly increasing. Similarly, if f dash x less than 0 for all x in the interval excluding the endpoints, and f is continuous on the interval, then f is strictly decreasing function. Now I have a question that to all of you, that if fx is strictly increasing, will it imply f dash x greater than 0? the question says that if the function fx is strictly increasing, then can we say that f dash x greater than 0? So the answer is no. We can take an example which is strictly increasing, but its derivative need not to be greater than 0. So let us take fx is equals to x cube. Then we know that f dash x is equals to 3x square and f dash at 0 is equals to 0. And from the graph, this is the graph of the function fx is equals to x cube. This is the point x is equals to 0. And from the graph, we can see that the function fx is equals to x cube, increasing at the point x is equals to 0, but the derivative of the function at 0 is equals to 0. So this is the function which is increasing at the point x is equals to 0, but its derivative at 0 is not greater than 0. So now we have two more important things that we have seen that if we saw that if f dash x greater than 0 implies that the function f is strictly decreasing, but the reverse part, if the function is strictly increasing, then will it imply that f dash x greater than 0? This is not true. That if I will make this condition correct, if f dash x, if fx is strictly increasing, this will imply that f dash x greater than equal to 0. We need to mind that the equality of the derivative, equality of the derivative happens at the discrete point. It cannot happen throughout the interval. If it will happen throughout the interval, then the function need not to be increasing function. So one more important thing is that I will draw the graph of the function which is increasing, but the derivative is equals to 0 at an interval. So let us see. So this is the point x is equals to a, this is the point x is equals to b. From the graph we can see that this is the graph of the increasing function, but the function is constant in the interval x is equals to a, and we know that the constant function has derivative 0. So f dash x is equals to 0 for all x belongs to interval a comma b, but the function is increasing. So we need to mind that the derivative becomes equals to 0 at only some discrete point in case of strictly increasing function, but in increasing function the equality of the derivative is equals to 0. It can happen at a discrete point or throughout the interval. So that's all for today. Thank you.